Have you ever wondered if the universe came with, an instruction manual? A rule book that explains how everything works, from a ball you toss in the air to a star billions of miles away? Well, guess what? It does. We just call it physics. And today, we're going to open up the first few pages.
So, for this explainer, we're getting our hands on a really unique version of this manual. We're looking at the universe through the eyes of a grade 11 physics teacher guide from the Ethiopian Ministry of Education. It gives us this incredible window into how the fundamental rules of the cosmos are taught.
All right, so let's crack this thing open and see what it says its mission is.
The first thing you notice is that this isn't just about memorizing a bunch of formulas. Nope. According to the guide itself, the real mission here is to build a whole new way of thinking. It's about learning to appreciate the world around you, to think critically, and maybe most importantly, to tell the difference between what's real and what's not. It's basically a toolkit for understanding reality itself.
But, before we can really start reading this manual, we need to learn the language it's written in. And for physics, a huge part of that language is math.
And one of the most important words in this new language is vector. Now, it sounds all technical and complicated, but the idea is actually super simple. A vector is just anything that has both a size, or magnitude, and a direction. Think about it. The wind isn't just blowing, it's blowing at 10 miles per hour to the north. A push isn't just a push, it's a hard push forward. Those are all vectors.
And this is where that language becomes so powerful. Now, don't get bogged down by the equations you see on screen. The big takeaway here is that this system of math lets physicists take all these real-world things, like two different forces pushing out an object, and calculate exactly what's going to happen. It turns a messy, chaotic reality into a clean, solvable problem.
Okay, so now that we have a little bit of the language down, let's see how we can use it. We're going to take that idea of vectors and apply it to something we can all see and feel, why things move the way they do.
So, you've got a box sitting on a ramp. It seems kind of complicated, right? You've got gravity pulling it down, friction holding it back, the ramp pushing up. How in the world does a physicist even begin to make sense of all that?
Well, step one is, honestly, it's brilliant because it's so simple. They just draw a picture. It's called a free body diagram. They get rid of all the extra stuff, the ramp, the background, everything, and just draw the object as a simple dot. Then they draw arrows to show all the forces acting on it. It just completely isolates the problem.
And once they have that clean, simple diagram, that's when they bring in the big guns, the fundamental laws of the universe. In this case, Newton's second law. You've probably heard of it, F equals ma. They apply that universal rule to the arrows in their diagram, and just like that, they can build an equation that describes what's going to happen next.
And this just perfectly shows the power of this method. I mean, it doesn't matter if you're looking at one little block on a ramp or a much more complex system with pulleys and weights and all that. The basic approach is exactly the same. You diagram the forces, and then you apply the laws. It's like a universal problem-solving engine. Now, what's really cool is that this same engine that helps us understand the world we can see, well, we can also use it to explore a world we can't see, the world of electricity and magnetism.
So, just to get our bearings, let's do a quick comparison between two of the universe's most important forces. We all know gravity, right? It acts on mass, and it always pulls things together. The electromagnetic force, though, is a little different. It acts on electric charge, it can both pull things together and push them apart. And get this, it is way stronger than gravity.
And just like Sir Isaac Newton gave us a law for gravity, a physicist named Charles D. Coulomb gave us a law for the electric force. This right here, Coulomb's law, is the fundamental rule that tells us how charged particles interact. It's another key page in our instruction manual.
Right here, this is the most amazing part. Just look at these two diagrams from the textbook. On the right, you've got that block on a ramp with forces like gravity and friction. On the left, you've got a charged little sphere just hanging in an electric field. I mean, they look like completely different worlds, right? But the method to solve them? It's identical. You draw your free body diagram, you identify the forces, and you apply the fundamental laws. The situation changes, but the logic, that language of physics, it stays exactly the same.
And this all brings us to a really beautiful final thought about this whole instruction manual for the universe.
You see, the rules we've been looking at, they aren't just for Ethiopia. They're for everyone, everywhere. The laws of motion and electricity don't change whether you're in Addis Ababa or on the moon. This whole quest to understand how things work, this process of observing and simplifying and calculating, it's a shared human thing. It connects a classroom in one part of the world to a high-tech lab clear across the planet.
These core principles, vectors, Newton's laws, Coulomb's law, they are the absolute bedrock that all of modern technology is built on. They're the first few chapters in our universal instruction manual. So the only real question left is, what mysteries will the students learning from this guide today unlock with them tomorrow?